Morning class, here we are ready to wrap up our last new lesson on chapter 8. I hope that you're doing well today and praying for a good day for all of us and just for all the pieces to fall into place for everyone. Here we are with complex numbers today. We've dealt with these pretty extensively in Algebra 2, but just to bring this back into the forefront and get us to a good graceful stopping point in the year, we need to finish this off and then do some things in Chapter 9, and then we'll be ready for finals and be done. So here we go. So first of all, we need to review that an imaginary unit, is represented by an I, and it means the square root of -1. Because any real numbers that you multiply together are not going to give you a negative. They're always going to give you a positive. So our definition of an imaginary unit is the square root of -1. And if you square a square root, you get the number back. So I squared would be -1. So that means that anytime you have a positive number underneath the radical, if it's just a square root, then you can bring an I outside. Now keep in mind this only works for square roots. It is not applicable to cube roots, and fourth roots are something completely, again, that we don't even have to deal with on these. So this is specifically a trait for square roots. So for example, when you're trying to solve the square root of 100, square root of -100, you'd bring the I out first, and then you would think about what number the square root of 100 would be. Now, a lot of times what you'll do is you'll go straight from here to here without stopping at this point. But you're really thinking, okay, I see a square root of a negative. That means I have an I come out. Same with this. We have the I come out. The negative number outside is something completely different. And then the square root of 36. So -6i. These imaginaries don't have to be super complicated. This one we pop out the I, but the square root 2, the 2 doesn't have a simplifiable radical, so there's no doubles, there's no perfect squares, so you have that. And then finally on this one we can bring out the imaginary part and then think of the factors of 54. We get 9 times 6 is 54, so that's 3 3s and a 2. You're looking for pairs, so 1 3 can come out, and when we write this, we write the real number first and then the imaginary and then the radical, so that it keeps organized, so that there's no question about whether the I is under the radical. An I under the radical is just a very, very weird thing that we're not going to even deal with. So if you have an imaginary part, always drag it out into the front of your multiplication problem, and the real number part goes even before that. All right, so that's how you've got that worked out. Now we do have that product rule that we said technically, and a lot of times people forget that technically it applies when you've got a positive underneath of the square root sign. Okay, so what you need to do first is you need to bring the I's out. You can either do it this way, where you bring the I's out and then you apply the product rule, and be very careful when you have I squared. Remember, I squared equals -1, so you want to replace that I squared with -1. So this is really just -6, okay? Because if you went ahead and you did square root of 36, you would get regular 6, but these imaginary numbers change that around, so don't neglect to pull those out. Or you can do this like this and simplify each one first. This one's 2i, this one's 3i, which gives you 6i squared, which once again, when you replace the I squared with -1, you get -6. So whichever is more convenient. Now in this case, it was probably a little more convenient to simplify first, because both of these are perfect squares with the negative. But in other cases, it may not be just as simple to do it that way. So let's take a look at some more examples. All right. Now, on this one, there's no perfect squares, so we're just going to bring those i's out and get I squared of 21. 21 doesn't simplify. I squared turns into a -1. So at the end, always look for your hidden I squares, because you do have to simplify completely and turn them into -1s. Over here, we could simplify this first, but it's going to just make things more complicated. So we can bring those i's out. If they're not perfect squares, it's usually simpler to bring the i's out first, because look what happens here. This one becomes very nicely just a 4, and this becomes a -1. So our answer for this one is -4. This one, there's an I for this part, but not for this part. So we're going to have an I in the number. A regular I does not get replaced with anything. It's just itself. And the square root 5 and the square root 6 go together and can't be simplified. So our final answer is I square root of 30. So when you're done, you may or may not have an imaginary part if you start with imaginary things to multiply together. Okay, so be careful of that. Now we come around to the idea of these radicals and dividing. So when we divide, once again, the quotient rule is the same. You have to deal with the imaginary parts first. So I can deal with this imaginary part, bring those out. Now, even though they're imaginaries, an imaginary over an imaginary will cancel out this imaginary part. Okay, our square root 75 over 3 can turn into the quotient rule, so you can go ahead and combine that, and then the square root of 25 is easy to find as a 5. On this part, let's work to simplify the numerator, bring the I out, and then apply the quotient rule. 32 divided by 8 is 4, and we end up with 2i. So that works out very nicely, even though we saw a radical in the denominator at first and thought maybe that was going to be a problem and we'd have to rationalize a denominator. Try all the other things first, and you'll probably find that things get much simpler, or a lot of times you'll find they get much simpler earlier. Okay? Now, this part is an imaginary. Whenever you have an imaginary I or a number times that, that's called an imaginary. A real number is just a real number. But when you have a combination by adding or subtracting of a real part and an imaginary part, we get that as a complex number. Okay, even if the real part is just 0 and it doesn't look like it's showing up, we technically have a complex number. So real plus imaginary makes a complex number, and when you're doing operations with them at the beginning, you kind of almost think about this as being, the I as being a variable. And if you think about the I as being a variable, you're most likely going to get all of the right steps until you have to deal with the final simplification. So, for example, here, when I'm taking a binomial plus another binomial, it's not really a binomial, but it looks like one. It's a complex number. There's a real part and an imaginary part, a real part and an imaginary part. The real parts gets added to the real parts, and the imaginary parts gets added to the imaginary part. So 2 and 4 is 8, and 3 and 4 is 7. So real part and imaginary part at the end. But honestly, if you didn't even know anything about that, and I told you to do this problem, you would get the same answer without even knowing anything about imaginaries, because you think of it as a variable. Okay, so think about them that way. If we have this whole sum right here, and you're trying to add them up, or even if you were trying to subtract them, if you were trying to subtract, you distribute the negative and just treat them as if they're completely variables. So you would put your 4 and 3 and negative 6 together, and the 2i minus I and the 3i together. And once you have that, 4 and 3 is 7, minus 6 is 1. 2 minus 1 is 1, plus 3 is 4. So you end up with 1 in the real part of the answer and 4i in the imaginary part, so our complex answer of 1 plus 4i. Now what makes it look a little bit different than if the I was just a variable? Traditionally, if it was a variable, you would put this part first, but whenever you're giving an answer to a complex number, put the real part first and then the imaginary part. Real part, then imaginary. And that's your standard way of writing a complex number, is the real part, then the imaginary part. All right, like I said, when we subtract, you do have to be careful that you're going to distribute that negative just like always. So there's our negative distributed. And then you put the like terms together, or you put the real with the real and the imaginary with the imaginary. 6 minus 3 is 3. 5 minus 2 is 3. So this giving us 3 plus 3i. Once again, distribute your negative. Then 7 minus 8 is negative 1. Negative 3 plus 6 is 3. So negative 1 plus 3i. Okay, right on with that. So we did adding, we did subtracting. We need to get a little multiplying in here. You can multiply by distributing, or multiply by distributing twice if you've got what looks like binomials. So here when I distribute, I end up with 8i plus 12i squared, but always at the end, if you have an I squared, replace it with a negative 1. So 8i minus 12i, minus 12, 8i minus 12. But the minus 12, remember I said in your final answer, the real part has to come before the imaginary part. So when you enter this on a test or a quiz, always put the real part and then the imaginary part after. Real, then imaginary. When you do this, you're distributing twice, or some people like to think of it as FOIL, but the 3 gets multiplied by the 4. 3 times negative 2i. 12 minus 6i. 20i minus 10i squared. What we did next is I put the like terms together. The imaginary and the imaginary went together, but we have this little I squared you have to deal with. The I squared turns into a negative 1 always. And then negative times negative makes positive. Then we've got 2 real parts that can get put together, which gives you a 22 in your reals and 14i in your imaginary. So this is your complex number that's the solution. Once again, 2 minus 10i plus 3i minus 15i squared. I squared gets replaced with negative 1. And then simplify, so you're ending up with a real and an imaginary. Okay, and that's your complex number. When you have a number, a complex number and its conjugate, remember conjugates in binomials were just where you had the same beginning and end and a plus in one and a minus in the other. And it's really, if you were going backwards, it would be a difference of 2 squares if we were thinking of it in terms of factoring. But this rule applies to complex numbers as well. So when I have this, if we think about distributing everything out, the middles drop out, so we end up with 3 squared minus 2i squared. You're always going to have a minus in between, and then whatever number is here, whatever thing is here is what gets squared. So we have a 9 minus 4i squared. 9, 2 and 2 is 4, I squared. Then you're going to replace your I squared with a negative 1. So it becomes 9 plus 4, which is 13. So whenever you multiply a complex number times its conjugate, you're going to get just a real number as a solution. That will be helpful when you need to divide out and you're dividing a complex number by a complex number or a real number by a complex number. But that complex number in the denominator, in order to make sure you don't have a complex number in the denominator, just like we didn't like radicals in the denominator, we don't like complex numbers in the denominator, so we need to use conjugates to get rid of them. So you look at your denominator and you figure out the conjugate, which means you make it into a minus. Anything over itself gives you a 1, so this is legal to multiply this by 1. It keeps the same value. Our numerator, we need to distribute twice, okay, like this. So our 40, our minus 16i, our plus 45i, our minus 18i squared. Here, 5 squared minus 2i squared. And when I do 5 squared, I get 25. When I take 2i times 2i, I get negative 4i squared. You need to begin to simplify this numerator, and you need to begin to simplify the denominator. Notice what happened. The like terms got put together, so imaginary went with imaginary. The I squareds had to be replaced with negative 1s. Then when you multiply them by negative 1s, what we end up here is a plus 18. So 18 plus 40 is 58. 25 plus 4 is 29. Now, you might think, okay, I'm done, but the thing is if we separate these into its two fractions, and when you're dealing with getting a complex answer, you do have to finally simplify it by separating it into its two fractions. You can either do that first and do 58 over 29 and get 2, and 29 over 29 and get 1, or you can factor out the common factor if there is one. 29 was in common here and it canceled on the outside. So when you're done, you're looking for a complex answer at the end so that you've got a real part and you've got an imaginary part, and the real part always comes first. Here we have a conjugate of the denominator. This is really 0 plus I. So that means our conjugate is 0 minus I. And 0 minus I is just minus I. So our conjugate that we're multiplying numerator and denominator by is negative I. So when I put that in, distribute that in, I got a negative I squared in the denominator, and I have this I that got distributed here. Now the reason that we would multiply by negative I is because when we turn that into a negative 1, this turns into a positive 1, which is very convenient because anything divided by a positive 1 is itself. But just remember when you write your final answer to put the real part first and the imaginary part second. So this is 1 minus I divided by 1, which gives you 1 minus I. Okay, so back to here, you're thinking conjugate of the denominator. And you do that to numerator and denominator. Here, conjugate of the denominator, even though it's a little simpler looking. Okay. Now, we need to be able to simplify powers of I that are I to the first is just I to the second is I squared. But we need to be able to think about what happens when we get I to the third or I to the fourth power. Okay, I squared is I. I to the third is really just I squared times I, which -1 times I. I to the 0 power, just like anything else to the 0 power, is 1. But so is I to the fourth power. And then what happens is it begins to cycle back down, around, and around, and around. Because I to the fifth power is really I to the fourth times I. So that brings it back up to here. And we're going to use that fact in order to figure out what happens when we have a giant power and a really nice shortcut. So I'm going to show you the long way first. Okay, groups of I to the fourths. Each time you have an I to the fourth, you get a 1. Okay, so when I look at this, and this is kind of, like I say, I'm going to show you a shortcut. I to the fourth to the 18th power. Wait, how much is 4 times 18? Let's just get a dumb calculator here so we can do this. Okay, 4 times 18. 72. Okay, so I've got 72 of my I's here and 3 more of my I's here. But I to the fourth power is a 1. So what that means is I have 1 to the 18th power, which is just a 1. I to the third power is -I. You're going to want this little table right next to you anytime you do these type of problems, whether it be on your test or whether it be on your final. You can have that. I'm upgrading it to note sheet next to you so that you can have this chart as part of it. Definitely include this chart. So this becomes -I as your answer. This is a long road to get here, but I wanted you to see that when we have any groups of I to the fourth, it is a 1. So what we can do in order to find the answer to this, rather than have to go through all this, what happens is that since every group of 4 of them just gives you a 1, no matter how many times you multiply 1 out, you're going to get a 1. And so the 1 just kind of gets swallowed up in it and disappears. So when I divide whatever power it is by 4, I'll get a whole number. And really, you know what? I don't even care about the whole number. What I care about is the remainder. So I get 75 divided by 4, and I get 18. And when I subtract that out, I get a 3. So I don't even care about the 18 ones. What I care about is the remainder, so it's I to the third power, which is -I. So our shortcut is going to be to divide this exponent by 4 to make it into one of these scenarios. Okay? And this is just saying what I just said. So we're going to be taking our exponent divided by 4, and our remainder is going to be the most important part. It's kind of one of the biggest things that we can do with the remainder that you might not have thought of as important in the past. Okay, so let's just run through these. So if I want to find I to the 39th, okay, oops, I didn't mean to do that. We divide out. Okay, so we're dividing. 39 divided by 4 gives me 9 with a remainder of 3. So that means I to the 39th power is I to the third power. And I to the third power simplifies to -I from your little chart. We divide out 54 divided by 4. The remainder is 2. Let me show you a little shortcut to that too. Okay. What you can do, it's easier on the other calculator, so I'm going to show you the other calculator because there's not a fraction button on this one. So let's go to this calculator. I'll show you a shortcut. Okay, so 54 divided by 4. Okay, so 13.5. We don't care about the 13 part, so I'm going to subtract it. We care about the remainder. We care about the fraction part. And if you don't know how to make that into a fraction, we care about the 1/2. We care about the remainder of 2. Now this half kind of makes it a weird looking remainder. So the fraction part isn't really even the best way on this. But what you can do is you can even use that 13 and go 4 times 54 minus 13 times 4. You've got your 13 whole number times 4. And that gives you your remainder 2. And this might be a little obscure. You're probably best going old school on this for your division. So you divide out, you find 13. Your remainder is the important part. So 1 squared, I squared is -1. On here, we have 40 divided by 4. My remainder is 0. I to the 0 is 1. That one's done. So if it's an even multiple of 4, you get a 1. 13 divided by 4 gives you a remainder of 1. So it's I to the first power, which is just plain I. So you could come out with any one of the 4 scenarios. You take your exponent divided by 4, and your remainder gives you which one of the 4 possibilities that it might be. Let's do another one just so that you can see. I don't want that. Goodbye logarithm from the other class. Here we go. So if I wanted like I to the 385th power, I would take 385 divided by 4. Okay, well, let's see. 4 goes in 9 times here. Bring down the 5. 4 goes in 6 times. Remainder is 1. So it's I to the first power. Okay, now say you're not really the best at this. Okay, so let's look at another calculator trick that you can do. Okay, I'm going to use the dumb calculator here rather than the smart one. Or the easy one, or whatever you want to call it. Don't want to. The one that's not that one. So we have 385. You do kind of still have to keep track of what you're doing. Divided by 4. And so I take 385 divided by 4. Plain basic calculator. I know it's 96 with something left over, so I've got 96 here. Okay, rather than having to go through the individual steps, you can take 96 times 4. 384. There's your remainder. That's your important part. So that's like a quick shortcut if you're not liking to do the longer way. You can find your whole number part, multiply it times this, and then subtract, and it'll give you your remainder, which gives you your exponent. All right, so there we have it. That's how you do all of these different things with imaginary numbers, reviewed back over what we did. So now your job is to work on your assignment, get yourself ready. We are headed for your test. Remember, we have Take a Break Wednesday in there. So tonight you're doing assignment 71. Tomorrow you're going to work on the Chapter 8 test review. And it's one of those where you do the problems that you need to do and then fill in a for your test. That will be your time spent tomorrow. But tonight you do need to do that homework assignment number 71 and get that done. All right, everybody have a great day. God bless you.